So I study chaos and I like chaos. So when other people start to run away, like in fear or anger, I pick up my notebook and start taking notes and start to enjoy things. So what I'm going to do is today is to share with you my intuition when I have to run too. Like complex systems, people like to study forest fires. So if everybody is running in this direction, we go in this direction towards a fire. But at some point, we have to run too. So to find out when you really have to run, this is what we are doing. And we try to forecast, predict catastrophes, earthquakes, explosions, all the things a little boy dreams of doing. Okay, and so I'm very fortunate that I'm sort of paid to play for all of my life. So this is sort of a good, nice secret which we shouldn't share too often. That if you want to be playing for all of your life, you should become a physicist. Okay, so today I would like to share some of the things I'm doing in my lab. And I would like to give you some intuition too. So we study complex systems. The first question is, what is a complex system? So I would like to hear from you what you think is a complex system. So when do you say the system is complex? And I want to have about 5 or 10 definitions from you, and then I give you my favorite definition. We check how consistent they are. Because often scientists define something and it has nothing to do with the real world meaning. So I want to do a reality check with you. What is a complex system? I would like to have maybe 5 or 10 suggestions. Yes?
A lot of interaction between particles.
A lot of interaction between particles. Between particles. And could you please tell me your name, first name? Oh, this is difficult. Like, yes, like this? Is that sort of correct? Okay. Other suggestions. What is a complex system? When do you say this is complex? Yes?
When it has multiple seemingly random inputs.
Multiple seemingly random inputs. And could you please tell me your name? First, Bob. Okay. So, other definitions of complex systems. I would like to have 5 or 10. Yes?
Something that has simple behavior sometimes and unpredictable behavior other times.
Wow, this is a good definition. You simple, sometimes. What was the second phrase? Behavior. Simple behavior. And what the rest of the time?
Unpredictable.
Unpredictable. Predictable. Else. Okay, other definitions. Oh, what may I ask you for your name?
Jim.
Jim? Okay, other definitions. Yes, there was some.
It's a zero-sum game for a reaction. There's a reaction, and a reaction to that reaction, and a reaction to that reaction, and it happens in perpetuity.
Okay. Okay. Reaction of a reaction of a reaction. Da, 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 da. And may I ask you for your name? C-A-M. Okay. Maybe a few more definitions. When do you say this is complex? Or what is an opposite of complex? Simple? Not simple? Okay, not predictable. And who in there?
Sabrina.
Sabrina? Maybe 2 or 3 more definitions of complex systems. Yes? Snowflake formation. This is a definition by example. Snowflake formation. May I ask you for your name? How to spell? G-U-S. Okay. 2 more. Definition of a complex system. When do you say this is complex? Yes?
Linear, nonlinear characteristics.
Okay. Linear and nonlinear. May I ask you for your name? Rick? Okay. 1 more. What is a complex system? Yes?
Predictable, only probabilistic.
Oh, that's a this is predictable, only probabilistically. Probabilistically. Okay, this is a good set of definitions. And now I share my favorite definition. A complex system is a system with a large throughput. And this throughput could be energy, it could be a fluid flow. So something comes in, but then if you put something into the system, something out has to come out too. So what we do is, in order to make a system complex, we ramp up the throughput till something spectacular happens inside. And this spectacular is called an emergent structure. Scientifically, those systems are often called dissipative. Open dissipative system. Open, means you put something in. Dissipative means something else is coming out. Open dissipative system. Systems with a large throughput. Now, every area of science, of physics, and this is a physics definition, has a key control parameter which is particularly large. Like in astrophysics, distances are very large. In quantum physics, temperatures are very low. In nuclear physics, the energy density is very high. Now, high and low is relative. Like the temperature is low, you call the temperature is low whenever quantum phenomena occur. And this could be like 2 million Fahrenheit at a nuclear star, at a star, or this could be a very low temperature compared to human temperature scales for some metal. So large is relative. Large is whenever the flow produces something spectacular. Now what are those spectacular things? So let me give you some example. For example, if you have energetic chemicals, then the result, what can happen is something like a flickering flame. And so we study flickering flames. And actually I brought a candle. I like candles because flickering flames are really cool for many reasons. So just to illustrate that, I brought a candle. I hope we don't set off the sprinkler. Okay, that's small enough, should be okay. And if though, we have chaos, and that's cool too. Okay. So another flow could be, for example, a fluid flow. And if the fluid flow is large, you get turbulence. If the relative motion of tectonic plates is large, tectonic plates, then we get earthquakes and other earthquakes. If the electrical current is large, we get lightning. and so forth. So if the traffic is large, we get stop and go motion. If the tension is large, which is a more abstract flow, we get fracture. If the fluid flow is large, we get turbulence. If the heat flow is large, we get boiling. If there's a lot of rain and snow, we get avalanches. If there's enough food, sufficient amount of food, we get life. And if the information flow is sufficiently large, we get computer crashes. Okay. Now, traffic is not necessarily a complex system, because if you look at, say, interstate at 2 a.m., you get one car and then you get nothing for a long time. You get another car and then you get nothing. I wouldn't call that a complex system. But if the traffic is large, like during rush hour in Chicago, where the traffic develops some stop and go motion, then I would call that a complex system. For the same reason, computers are not necessarily a complex system. Just if you open one application, and then you open a second application, and then you open a third application, and so on, eventually you may make the computer a complex system, and it behaves in an erratic fashion. A lot of people think that computers are complex systems because if you have Windows, it becomes erratic already when you open the second application. Okay, so let me now check how well those definitions fit with your definitions, how this definition fits with that definition. By the way, other fields of science have other definitions. Like in computer science, complexity means that it is a complex algorithm. The complexity of an algorithm just means that how much computer time you need to evaluate it. In mathematics, there are complex numbers, which have nothing to do with that definition as far as I can tell. So different fields have different definition of complex systems. So I'm giving you a physics definition of a complex system. So often the particle which the systems which we study have many parts. So I may add that. And we look at the patterns which are formed by those many parts. So we often study open distributive systems with many parts. And in this sense, Cashier's definition fits. Multiple seemingly random inputs, outputs, inputs. Those systems often behave in an erratic fashion. So what we do is, those systems behave in a similar way. You can use similar mathematical tools to describe those systems, at least the emergent structures. So the mathematical tools that we use are, for instance, deterministic chaos, which is a mathematical concept, or cellular automata, or fractals, the theory of fractals, or the theory of neural nets, or the theory of genetic algorithms. And we use those mathematical tools to describe properties of the complex system. And so properties of complex systems are, for instance, that they try to minimize the resistance. So when you push something through like a fluid, the system tries to minimize the power consumption automatically without us doing anything. Or the system, another phenomenon is that the system reacts most sensitive to its own dynamics. If you mirror its own dynamics, you get the largest response from the system. Another thing we observed is that those systems, when they are self-adjusting, they tend to avoid chaos. So if you let the system alone, like this one, chaos goes away. So what this system is just a video screen and a video camera, And what I do is I take the video signal output from the camera and feed it back to the screen. And then the camera, it takes a picture of the screen, and so this goes back in a loop. And so this is an open dissipative system, makes interesting patterns like this. So this is live, or if you just walk by, you see. But if you let it evolve, after a long time, the chaos which you see now fades away. And so those systems tend to avoid chaos. But we developed some statistical methods to predict chaos, and actually this is predictability only probabilistic, so this fits very well. And another phenomena is that the whole is bigger than the parts, because in those systems, often the shape of the container determines the behavior inside. Like if I change the container a little bit, the shape of the container dominates the behavior inside. So in this sense, the whole is often more important, is more than the sum of the parts. There are some methods for controlling chaos. Another observation is by Stephen Wolfram that discrete mass provides often better models than calculus-based models. We observe that fast dynamics often entrain slow dynamics. So if you have two competing agents and one agent is a bit faster than the other agent, the faster agent usually takes over control. There's a leadership paradigm which says that if you have two competing agents and one agent wants to impose chaos on the to-be-controlled system, and the other wants to impose order, usually the natural system listens to the agent who wants to impose chaos and ignores the agent who wants to create order. Why is that? Because orderly behavior is exploitable. Repetitive behavior is exploitable. And therefore, the agent who wants to impose chaos usually wins in the competition. And then what we observe is that those complex systems often don't move smoothly. They sort of jump. They do a stop and go motion. So stop and go motion and avalanches are very typical for complex systems. So these are some of the things we managed to describe using these mathematical tools. Okay, so do the definitions fit? They have multiply seemingly random outputs. I would agree with that. The dynamics is chaotic, irregular. Like here, we have a water wheel. This is a water wheel. Like some water is coming in and the wheel turns to the left or to the right. And imagine you have to predict the next 5 turns. This is the smallest vibration in the room can make it turn the other way. And so this is, in this sense, the output is random, seemingly chaotic. And so this fits. And simple and sometimes unpredictable behavior, like when the wheel is at rest, the behavior is simple, but then it's turning, which is complicated. The reaction of a reaction of a reaction, this is what you see here. And so I agree with this. There's often feedback in the system. Inside this system, there are feedback loops which make it nonlinear. And this is because the throughput is so large, feedback becomes impossible. Now, it's not simple and not predictable. I will show you today that some aspects of the system are often predictable and the others are not, and we need to find out what aspects of the complex systems are actually predictable. And I will show you some experiments on that. So a snowflake formation is like formation of a fractal. This is some of the key things we study in complex systems. And because of internal feedback loops, those systems are often nonlinear. So this is feedback. Feedback is important. The throughput is so large that we get that feedback becomes important, and this makes it nonlinear. Any comments, any questions at this point? Okay, this was a lot of theory. So now let's do some experiments. So one experiment that I brought, other than the water wheel, is an experiment which has a large electrical current. So let me explain that experiment a little bit. So what we have is here, the experiment consists of two electrodes, a high voltage electrode and a boundary electrode. So the high voltage electrode is powered by a battery, and then we have a petri dish. Inside the petri dish are metallic particle, is some castor oil, and this is a boundary electrode which is grounded. So the battery maintains a voltage of about 20,000 volts. The source electrode sprays from the tip charge on the surface of the oil. There's an air gap between the tip and the petri dish of about 5 centimeters. The diameter is about 12 centimeters, which is about 4 inches. The oil height is about 3 millimeters, which is like 2/10 of an inch, enough to cover the particles. The oil we use is castor oil because it has a high viscosity, low ohmic heating, and is biodegradable. You can eat this experiment if you want. Most of our experiments are edible. Okay, this is important because they are often so messy, so you don't want to handle poisonous stuff if you do a messy experiment. The particles are non-magnetic stainless steel, and they have a diameter of 1.6 millimeters. Okay, and now I'm showing you what you get. So let me switch the... Okay, so I start out with random distribution of particles. Okay, I take a clean sheet of paper. Okay, and then I switch on the non-equilibrium, like the voltage, and then I try to make it complex. So right now, I would need a volunteer. Okay, who would be willing? Yes, okay, please come down. So please raise the voltage in steps of 1,000 volts till you see something moving. Is there anything moving? So this is not a complex system yet. It's sort of regular physics. Anything moving? No. So this is how you make a system complex. You ramp up the throughput till something spectacular happens, or the experimenter turns pale. Okay, making noises, that is a good sign. So ramp it up a bit more. Yes, okay, ramp it up a little bit more.
Okay. This is its highest setting.
Oh, okay, then we have to wait. Okay, so you see that the particles agglomerate to tree-like structures. The trees are self-assembling, so you get self-assembling structures. Stable, like if you break one of those structures, like a small gap here, and then I feed it again with energy, you see it's repairing. These are stable, self-assembling structures. Of course, if you make a big perturbation like this, it does not grow back to the same structure. It grows a different structure. But if you count the number of endpoints, you always get the same number of endpoints. So let me describe that real quick here. So if you get a structure like this, we have 3 different types of particles. We have the particles at the end which have only one neighbor, like the red ones. And then we have the particles, the trunks, which have two neighbors, like here. These are trunks. And then we have branching points, which have three neighbors. So we classify all particles in the structure into three classes: endpoints, branching points, and the rest. And when you run this experiment, you find that no matter how many ball bearings you have, no matter how much oil, no matter what material the ball bearings are, as long as they are conducting, you always get 22% endpoints and 22% branching points. And the rest makes connections. So this is very reproducible. So this system has some properties which are very reproducible. For instance, that the number of endpoints is always 22%. Another reproducible property is that this system does not form closed loops. Do you see any closed loop in the experiment? Okay, to check that the system indeed avoids closed loops, I make a closed loop. Like this. And then I power it again, and you see it opens up. This system detects closed loop and closed loops, and this is a remarkable reproducible property too. When you look outside and study the branches of a tree or the root system of a plant, you will almost never see closed loops. And so the question is, why does this structure form no closed loops? One of the answers is that almost all the current enters through the endpoints. And so when you break up a closed loop, you create two more endpoints, and this lowers the resistance. And this is another important reproducible quantity. If you run this experiment many times and you measure the resistance between the input electrode, the red one, and the output electrode, so, this one and this one, you find no matter what you do to the experiment, you always get the same limiting resistance. And during the experiment, the system tries to reduce the resistance. Reducing the resistance means minimizing the power consumption. So this system has a tendency, if you let it, to minimize power consumption. This is cool, isn't it? So let's say if you would let your car optimize itself, it will become more energy efficient. If you let your washing machine optimize itself, it will become more energy efficient. So there's a natural tendency to become more energy efficient, and Ilya Prigozhin discovered this in the 70s of the last century, and he won a Nobel Prize for that. He discovered there's a natural tendency for complex systems to minimize the energy consumption. Nobel Prize in complex systems. Ilya Prigozhin. So in this system, there are reproducible properties. But there are other things which are not reproducible. And for instance, if you disturb the system, like if I choose a slightly different initial condition, or if I choose a different initial condition and I would move one of the ball bearings a tiny little bit, I get a different structure. So the system is sensitive to the initial conditions. The trees which are forming are never the same, and even if you try to make it the same, even if you try to put the ball bearings exactly at the same position, you don't get the same trees. Like the branching pattern is different, except that we always get 22% endpoints and 22% branching points. By the way, biological systems tend to have the same property. If you know the soil condition and the climate at a certain spot on the earth, you can predict the leaf area. Like if you would measure how many, the area of the green area of the leaves depends only on the soil condition. And now those leaves could be on a couple of tall old trees, or they could be on grass, or they could be on more smaller trees. But the leaf area depends only on the soil condition and the climate. And the leaves can be on different types of vegetation. So the type of vegetation, the size of the trees, that's history dependent. But the leaf area is not. The leaf area depends. Like in our experiments, the number of endpoints does not depend on the history, but some other things are, like the exact structure of the trees. So sensitivity to the initial condition means chaos. So let me show here a little experiment which illustrates that. This is a double pendulum, a pendulum attached to another pendulum. And such a simple system can make chaos, like can be sensitive to the initial condition. When it's sensitive to the initial condition, it's hard to predict. So let's say if you make a dynamics like this dynamics looks complicated, but complicated does not mean unpredictable. Unpredictable means, or hard to predict, or chaos means if you change the initial condition a tiny little bit, you get a different dynamics. So in order to check if this system is chaotic or not, well, I have two pendula, and I start them out with a similar initial condition. And I check if the two do the same thing, and I see, well, that's a complicated dynamics, but it's not chaotic, because similar initial conditions give a similar dynamics. This is not chaos. On the other hand, if you start up here, do a similar initial condition, right? You see you get a totally different dynamics. So this system, if you start up, the same system can be chaotic. Different dynamics for a different initial condition. What happened to this? Actually, I think this is cool. I like chaos. Look, imagine, turn it in the dark. This is in the dark. Follows the trajectory in the dark. This is really cool. High voltage in the dark is cool. Chaos in the dark is cool. You can hurt yourself. Like when you try to catch it. It's hard to catch chaos, a chaotic system. So the experiment, the ball bearing experiment, is sensitive to the initial condition too. If you change it a tiny little bit, you get a different structure. Now one thing which is really dependent on the initial condition is the number of trees. Like right now we have 1, 2, 3, 4, 5, 6, maybe 6 or 8 trees. If I start out from a different initial condition, I can show you, I can produce a pattern which has only one tree. So the number of trees is a property which depends on the initial condition, sensitive. And in this sense, the system is chaotic. So if you count the number of trees, you would say this is a chaotic system. If you count the number of endpoints, you would say no, that's not a chaotic system. So some aspects of this open dissipative systems are highly predictable and some other aspects are not. And it's hard to tell what is predictable and what is not predictable. And this is what we do in our research. We try to find out which aspects of the system are highly predictable and which aspects are not. And once you know that, you know much better how to deal with the system. I lower the electrode a little bit to speed it up. Okay, another volunteer. Who will be? Yes, please come down. So we make this system now complex, ramp up the voltage till you see something going on. Oh yes, I think you can stop already. So just wait. So we see linear chains of ball bearings. They are competing with each other. They all want to reach the grounded electrode. One of them will win. This will become the stem. The other chains will be destroyed by the system. And you see how they move the charge. It's sort of a bucket brigade. The other thing you should see is they do not move smoothly. They move and then they stop, and then they move and they stop. You see stop and go motion. You see a race. There's no branching so far. Who will win? Okay, one of them won, the other ones get destroyed, and now it's starting to branch out. And see, we have only one tree now. So the number of trees depends on the initial condition. Okay, what is your name? Nathan, thank you. So the number of trees depends on the initial condition and is not an easily reproducible property. I think those structures are pretty. And if you study them in more detail, you can show that they are fractal patterns. Fractal pattern means the pattern has a fractal dimension. So let me explain that a little bit. If you have a two-dimensional sheet, and you pick a point at random, and then you draw a circle with radius r around that point, and you ask how many other points on the sheet are on the sheet, how many other points are at distance r. So number of points on the sheet at distance r is proportional to r, because it's a length of the circumference of a sphere. On the other hand, if you have a one-dimensional sheet, like a line, and do the same thing, pick a point and then draw a circle, you find only 2 points at distance r, no matter how big the radius is. So if you do the following plot, if we plot here the number of points at distance r, and here we plot the radius, this is 2, so for a one-dimensional object, d is equal to 1. This is a constant. For a two-dimensional object, this is proportional to r. For a three-dimensional object, this is proportional to r squared. So the number of points at distance r is proportional to r to the power of d, where d is the dimension. And this is a way to define a broken dimension. You can even define negative dimensional objects with that. Now, in an object like this, if you pick a point at random and draw a circle, the number of points at distance r does not grow, is not proportional to r. It's a power law, but it has a different proportionality. And so, if you study this object, you find that the fractal dimension of the object is about 1.8. So, another way to look at this is a linear object, a one-dimensional object, every point has 2 neighbors. In a two-dimensional object, every point on a rectangular grid has 4 neighbors. But here, in this object, we have sometimes 3 neighbors, we have sometimes 2 neighbors. So it's not really a one-dimensional object, but it's also not a two-dimensional object. So it has a dimension between 1 and 2. And so this is another reproducible property of the system. Actually, I can show you some plots here. See, this is the number of endpoints as a function of the number of particles. This illustrates that you have 22% endpoints. But this shows the number of particles within a certain radius r and it shows that this goes like a power law, and therefore the object has a reproducible fractal dimension. And this is the fractal dimension of the endpoints, which is 2. So this means that the endpoints are homogeneously distributed, whereas the points which make the connections to the grounded electrode are a fractal. So you can make the following interpretation of the structure. In this structure, the endpoints are homogeneously distributed, and the rest of the ball bearings make shortest connections to the grounded electrode. So try to connect all the endpoints, and they form a fractal network. But the endpoints themselves are homogeneously distributed. See, I think these are pretty patterns. Those fractal objects have some aesthetics to it. Like a flickering flame is something nice, a fractal is something nice. Often the structures that we study are pretty. I think this thing is pretty too. Okay, next I want to show you I want to shift gears, and I want to show you one other property of this system. So now I move most of the particles on the side. I lower the electrode, and I mark 2 points on the paper, A and B. These are the points A and B. And I put a few ball bearings between A and B, like this, a few points. And I try to move the rest of the ball bearings out of the way so they don't interfere too much. Okay, and then what I do is I connect electrode B first, and I ramp up the voltage. And what you should see is that there's a wire forming. You see the wire forming? So this is a self-assembling wire. You may even see a little bit of lightning in between. And then I connect the other electrode, and you see another wire forming. So if I use electrode A a little bit, and then I use electrode B a little bit, you see you get a branched wire. Now if I use only B, if I use only electrode B, all the ball bearings are moving over, and the connection to electrode A is destroyed. If I use only, let me reduce the number of ball bearings here a little bit. So introduce more competition. So if I connect B only, connection A is destroyed. If I connect A only, B is destroyed. So if I use B a little bit, and then I use A a lot, then B a little bit, and then A a lot, you see the connection to electrode A is well formed, has many ball bearings, whereas the connection to the other electrode, which I'm using only occasionally, is not that well formed. This is called Hebb's learning rule. In your hippocampus, you grow every day about 10,000 neurons. If you use them, they stay. If you don't, they will die within 2 weeks. And if you use one of your neurons a lot, it is strengthened. That's Hebb's learning rule. Hebb discovered that many years ago. And so what I'm showing you here is that this system satisfies Hebb's learning rule. So this means, if it satisfies Hebb's learning rule, this means we could potentially build a brain out of that one. Okay, so how would we build a brain? Well, we would build a simple perceptron. A perceptron is like this. So you have a couple of inputs, like you have 1, 0, 1 as an input. And you want to have as an output, let's say, 1, 0, 0. And then you put a box with ball bearings in between. And the 1 means the electrode is connected. So the 0 means not connected, and the 1 means connected. And so the connection is, let's say, to 5 volts. At the output side, connected means grounded. They have a grounded electrode. Not connected means 0. 0, not connected. And then you put a whole bunch of ball bearings in between. And so what will happen if you have those 2 electrodes connected, the ball bearings will form a wire connection like this. What you do then is you may apply a different input pattern and a different output pattern, and repeat the input patterns and the output patterns, and the system can learn. That's a perceptron. Now when you look at the word perceptron, it's composed out of 2 words, like perception, which means understanding, and tron means machine. So this means we claim that we can build a machine that understands. Whoa! Can computers understand? Okay, so let's go back. What is understanding? So I want to hear from you, what is understanding? So let me move that up, and I want to do a definition of understanding. So some suggestions. When do you say I understand? And then we'll check if the machine that we try to build will satisfy your definition of understanding. So what is understanding? Or when do you say, I understand? Suggestions, please. Yes?
When I can reproduce it more than once.
Reproduce it more than once. Can reproduce it more than once. Can reproduce it more than once. Other definitions of understanding. What is understanding? Yes?
When the system gives you an appropriate response to your input.
Appropriate response. Appropriate response to input. Oh, what's your name?
Jim.
Jim. Thank you, Jim. And I forgot to ask, who made this suggestion?
Miriam.
Miriam. Thank you, Miriam. Okay, other definitions of understanding. When do you say I understand? What is understanding? We use understanding a lot, isn't it? Like, and in particular at the university, yes?
You can circumvent like a little trick thing in the middle. That means you really understand it.
Circumvent a little trick thing in the middle. Can you give me a shorter phrase?
So, for example, if someone gives you a question, which
Yes.
I have an understanding of it, but they phrase it in a little slight way,
Yes.
to maybe trick you. If you really understand it, you'll be able to see through that.
Oh, see through difficult phrasing. That's interesting. That's good. I have never heard that definition. It's cool. Okay, and may I ask you for your name? Rachel, yes, I should know that. Okay, other definitions of understanding. When do you say I understand? Suggestions. Or when do you say, what is the opposite of understanding? Is there an opposite? What is the opposite of understanding? Confusion. So, not confused. Okay, maybe one or two more definitions of understanding. What is understanding? Okay, I move on because we are running out of time. So I give you my definition of understanding. Being able to translate. Like I understand French or Spanish if I can translate from English into Spanish and back. I can understand the world surrounding me, like this is, let's say I see a bright light outside, and this is me. This is my head. Okay, and so there is a concept here which says sun, and if I see the bright light outside, I can match it. Match means to understand. And then I use my concept of the sun to predict that this bright light will be gone in 12 hours. So, or let's say this is physics. And so we have to add, this could be a practical understanding, practical concepts of physics, and these are abstract concepts of physics. Like a practical concept of physics would be push and pull. An abstract concept of physics would be conservation of energy. So I can have practical understanding of physics if I can translate an abstract concept into a practical concept. Or I have an abstract understanding of physics if I can translate abstract concepts, practical concepts into abstract concepts. Or if you have another set of concepts like biology, this is physics, and let's say math, it works easier with math. You can have a mathematical understanding of biology if you can translate a biology problem into math, solve it in mathematics, and translate it back. Then I would say, so understanding is always something in terms of something. It means being able to translate. Now I don't think it's my fault. There are different levels of understanding. Like there is a level of understanding of a first year of a foreign language, first year foreign language. This is like dictionary, a dictionary level of a foreign language. And like a C. elegans would have that. And let me plot here into this direction the number of neurons. And C. elegans has about 300 neurons, which corresponds to sort of a handheld calculator. C. elegans. And so the C. elegans has sort of a dictionary level of understanding, can process certain inputs, has probably, is a little warm, 300 neurons, like a mosquito. And then probably the C. elegans has no feeling for time and has no feeling for left and right. Can go in a certain direction, but okay, then there's the second year of a foreign language, where people learn grammar. They can have can process many more inputs, infinitely more inputs. It's like a difference between 1 and 2 dimensions. And this would, like, a C compiler could do this, C++, this level of understanding. And then there are other levels of understanding, like a third or fourth year of a foreign language. And this includes context, history, being able to translate a poem. And this is what humans can do. Computers are not quite there in terms of compute power. And humans have about 30 billion neurons. And then you can do, computers will be there in about 5 to 10 years, but they are not there in terms of compute power yet. So there are different levels of understanding, and there are sort of infinities in between those levels in terms of processing capability. But it's still translation. And so when being able to translate, if this means understanding, this is something which these machines, the perceptron, can do very well. It translates an input into an output. Okay, so you could say, so what? We build another brain. There's only one difference. Then the difference is that the particles which I was plotting there could be nanoparticles, which have a diameter a factor of 1,000 thinner than your neurons. So if this is a human neuron, so let's say this is a long human neuron, complicated neuron. This is a neuron, human neuron. You can fit inside a human neuron 1,000 by 1,000 by 1,000 atomic neural net neurons. Because the human neuron has a diameter of about 1 micrometer, whereas an atomic neural net neuron has a diameter of 1 nanometer, which is a factor of 1,000 thinner. And therefore you can fit into the volume, the space which is occupied by one human neuron, 1 billion atomic neural net neurons. Now how about power consumption? Well, the power consumption depends to first order on the resistance. Now, our human tissue is not a particularly good conductor, like not even a metal. So the energy consumption of our brain is about 60 watts, but it could be much less, because our human brain is not a good conductor. Now you can build those perceptrons you can use for ball bearings, and actually one of my students is doing this. He uses as particles in this experiment superconducting nanoparticles, which have a much smaller energy consumption than the human tissue. So what I'm saying is we could build now, with current technology, a brain which is the size of a human brain, but has 1 billion times more neurons and spends much less energy. Wouldn't that be cool? Okay, so let's go back. Where are we on that plot? Okay, so this is 30 billion and this is 300. And so the atomic neural net is sort of off the scale over here. Atomic neural net. Because it is 1 billion. 1 billion can have 1 billion times 30 billion neurons. And we can only speculate what will happen then. So probably there are other levels of understanding up there which are incomprehensible for humans. What does it mean being incomprehensible for humans? Oh, so just imagine the C. elegans or a mosquito would ask you, or would ask me, to teach her calculus or to teach her physics. The mosquito will say, I want to take physics 214 or 212, physics introductory course. What would I tell the mosquito? I would say, sorry little animal, this is a very noble effort that you want to learn physics, but you don't have the brain. You don't have enough. With 300 neurons, come on. Okay, so the relation between us and the mosquito is like the relation between the atomic neural net and us. So if the atomic neural net would make a prediction, say, okay, I come to the lab and I switch on the computer or look at the computer, and the atomic neural net would say, I have a suggestion for you. Do this experiment today. So why should I do this experiment? The atomic neural net will say, because last night I read 100,000 physics papers, which were published this year, and checked what is relevant to your research. And I checked the literature for the last 20 years too, 1 million papers. And I found an interesting correlation between the data you measured yesterday and data published in that paper 10 years ago. And therefore you should do this experiment. Would I do it? Probably. So the research would not be driven anymore by humans, but by an atomic neural net. And to a certain extent that has happened already. Because when I start a new project, I check Wikipedia, I check Google first, before I start the project. But so far, Wikipedia cannot read research papers. And this may change in the next 5 or 10 years. So atomic neural nets may use their compute capability to do something which is unimaginable. Will they be friendly? Okay, so I can imagine, like, they will need us to build them. Like we need cows for milk. So we are friendly to cows, isn't it? Usually, sort of. Sometimes. Okay, so this is one thing that will be friendly, hopefully. Can we avoid building them? I'm not sure. That's atomic neural. And actually, one of my graduate students was hired to build them by Cyprus chip manufacturer with a specific task to build atomic neural nets. So we can just hope that atomic neural nets will be friendly to us. Are you friendly to mosquitoes? Sometimes. Or no? But we are okay with C. elegans, I would say. So this is one thing. And now the other thing is that probably we will be immersed in a world which is combined out of those super intelligent systems and the real world. So right now, I think the picture will change. Right now, the picture is we are controlling the world. So this is the world, and this is us. This is us, and so we try to control the world. We try, at least. I think the picture will change. This is the world. This is us. And these are those super intelligent systems. And so we are much more part of the world. We are sort of subtly changing sides. We are on the other side. And so the world as a whole will be a combination of the real world and the virtual world created by super intelligent systems. How far are we with that? Okay, so let me show you it will take maybe 2 or 3 more minutes to show you something. So we are in our lab actually studying this. So what would happen if you combine the real world with the virtual world, like a real pendulum, like this one, with a virtual pendulum in an instantaneous bidirectional coupling? So those super intelligent systems will be on the alert and controlling us and taking data all the time. They are sort of fully integrated with the real world. So we expect that some new interesting states will emerge, which are sort of a mixture of the real world and the virtual world. We study those systems. And one experiment, which I think is really thought-provoking, is the following. If you play a computer game which is very realistic, where the people look like the real world people and where the houses look like the real houses, we predict that there is a transition where the player can no longer distinguish between the events in the game and the events in the real world. So what we predict is that that boundary between the real world and the virtual world will go away. And actually I brought an experiment. This is my last experiment, where we can sort of demonstrate this, hopefully. And this is this experiment. And I would need a volunteer, but the volunteer should be mentally stable and strong-willed, okay, because it's sometimes a bit challenging. So you could feel sick afterwards. So who is willing to do that experiment? So what we will do is we will try to give you an out-of-body experience. So who wants to get yes, please come down. Okay, so the experiment goes like this. Out-of-body experience is sort of a mixed reality set. So please sit down on that chair and look at the screen. Okay, and so what I will do is I will videotape you from behind. Okay. Okay. So you can see yourself now from behind, and then I will tap you on the shoulder like this. Can you see yourself from behind? So where are you? So do you feel something strange? Yeah. Okay. What's your name? Katerina. Okay. Yeah, Katerina. Okay. Thank you, Katerina. Let's try somebody else. So what I want you to do is that you have suddenly you are confused where you are. Are you, like usually people think their identity is somewhere between their eyes, and if you can see yourself from behind and see how you move from behind, suddenly you think you see yourself, you are outside your body. Now, with this little setup, with this simple setup, it happens only in 1 out of 3 cases, but if people use video goggles, like 3D video goggles, it happens almost ever. So I would need another volunteer. Let's try it again. One more. Volunteer. Yes, please come down. So this is sort of the third-person perspective in a video game. So please sit down. Okay, and so I'm videotaping you from behind, like this, and so you can see yourself from behind. Now, oops, I think maybe this is the problem. You cannot really see yourself. I need to be a little bit closer. Okay. I think I need to zoom out and focus. The color is important. It's important that 3D is much better than 2D. Okay. So can you see yourself from behind? How do you feel? Okay, almost. Not much. Okay. Well, what's your name?
Vijay.
Thank you, Vijay. Okay, so what can happen is that sometimes people have the feeling they can see themselves from behind, which makes them confused, and sometimes people are even throwing up afterwards. And so it's a very strong, it can be a very strong sensation, seeing yourself from behind, and then you don't know where you are, you're confused. Okay, so to sum it all up, complex systems is the science of open dissipative systems. You can do cool and beautiful experiments, but some of the stuff is also really scary, which is fitting for Halloween. Thank you very much.
Any questions for, yes?
I'd like you to say something about what the problem of teaching these extremely large systems accurately.
Say louder, please.
When we teach these extremely large systems, how do we make sure that what we told them is correct?
They teach themselves. I think by observing the world. Like nobody taught us how physics work. We taught it ourselves. But we observe, so those systems, you can show that systems can do happy and learning, can make abstractions, they can have frustration, but they can make abstractions. So they can detect correlations automatically. They do this automatically. So nobody taught us physics. We discovered physics just from observing the world. And those systems will have to do the same thing. They are not taught.
Does this mean there have to be more than years or supposed to be entirely?
See, we are very limited. We can only memorize 6 or 7 things at a time. Computers can memorize many more things at a time. So though computers can detect correlations which are very hard for us to detect. If you open a physics textbook, it has never more than 7 variables in it because we cannot memorize more than 7 variables. A computer can deal with concepts which are much more abstract than what we can do. And so we are sort of severely limited by our hardware. And so I think those systems can easily do what we do and more.
There's a question to the left.
Yeah.
What's the fractal dimension of intelligence, do you think, in terms of neurons?
Fractal dimension of intelligence.
Of understanding in your plot there of level of understanding versus neuron number.
The fractal.
You would think of that in terms of a fractal space.
I would have to think about that. Yeah. I think there are different levels of understanding, and so it's a good question. This is like 1D and 2D and 3D. And so I think one could possibly do a generalization, but it's a good idea, I haven't thought about it.
Any other questions? Or then we'll,
There is one.
Oh, okay.
Well, we have intelligent systems, sort of, that we talk to using a limited vocabulary. For example, when you're making a reservation for an airline ticket.
Yes.
And this seems to be the province of the artificial intelligence people. When do you think we're going to go beyond that and get into something a little more general and very specific vocabulary that we use for certain kinds of purposes?
See, the human language, like even computer languages, go beyond human languages in many ways, because in human languages we cannot nest, and in computer languages you can like nest inside a loop and inside a loop. So I think computer languages go in many ways beyond what human languages are do, but in some other ways they are not. going yet that far. Like they are not really context dependent, but they maybe catch up to become context dependent. So I think human language is restricted by the human hardware of the human brain, and you can build systems which go beyond, which are not, do not have those restrictions. Like in terms of what you can memorize, the sentences can have only a certain length. So I think human language is only relevant in the sense that we can interact with the system. So sort of the superintelligent system could have some thoughts which are incomprehensible to us, but if they want to talk to us, they have to boil it down to a language which we understand. But this doesn't mean they are restricted to that.
But it also has to understand the real world, and that's the hard part. Putting the real world into its knowledge.
Yeah, but we have to model the real world with equations which contain at most 7 variables because we cannot comprehend more. So the superintelligent system may come up with modeling techniques which are far more efficient than what we have, because we are limited by human thinking. So that the superintelligent system may be able to make much better predictions and find much more correlations in the world surrounding us than we can do.
I just hope the real world doesn't get reduced down to a smaller level so that the superintelligent system can manage it and won't be reduced to the same level.
The superintelligent system is part of the real world too. So it's just a difference of flower in the real world.
Two more questions. One at the back. Cashier, right?
Sure, yeah. So your explanation of understanding was translation.
Yes.
What you showed there seems to imply it is a matter of constructing an inverse function in some ways. That if you receive an input, but then you're able to go back and construct what you have sent out, that signal that you received. So you're basically constructing an inverse function.
Yes.
In that.
Yes.
And the higher levels of understanding seem to then be basically constructing not just the inverse function, but an associated set of facts that may be associated with the inverse function. So that
Yes.
context, history,
Yes.
all that kind
Yes.
of stuff. So when you then talk about higher levels of understanding,
Yes.
I'm not sure I really buy that, because our understanding, which is different from that of C. elegans, is because we
Yes.
have a whole set of facts associated with that input. Is there any other level of understanding beyond that, expanding that set of facts that you may be able to
See, I think understanding is often detecting correlations, detecting patterns. And so, like, push and pull is a very basic concept in physics. And then if you talk about Newton's second law, creates a relation between force, mass, and acceleration. And so this is a correlation between concepts. It's not really something which you cannot really experience the Newton's second law in real life. You can only experience a correlation between those quantities. And so you can go to higher and higher levels of abstraction by trying to detect correlations, relations between lower level concepts and on a higher and higher level. And so, for instance, when you study a physics textbook, we find there are at most a total of 7 levels of abstractions. There are 7 levels of abstractions. And maybe this has to do with the fact that as a human, we can only remember 7 things at most. I'm not sure I answered your question.
Okay, so this is really an appropriate Halloween
Yes.
subject, the creation of Skynet. So I'm sure there's probably a couple people who'd like to try the camera.
Mm-hmm.
So let's thank Alfred if there are no more questions.